Hello. Well, this begins Chapter 6, and Module 6 starts on page 177, and is called The Application of Newton's Second Law. And this is, Chapter 6 is really, could easily be connected with Chapter 5. It's really just a continuation of Chapter 5. So in Chapter 6, we're going to talk about really two different types of what we call equilibrium. It really comes under the heading, if you were an engineer, an engineering student, all of this would come under the heading of what we call statics. And statics is basically describing all the physics laws dealing with bodies in static equilibrium. And that's really the first half of this chapter is what we call translational equilibrium. Translational equilibrium. Okay, and this is talked about on page 177. And it's basically when we have translational equilibrium, when the sum of the forces, the sum of all the forces that act on an object are equal to zero. Now remember, we know that Newton's second law is F equal ma. So if the sum of the forces equals zero, then that means that the acceleration of this mass is zero. So this is what we mean by translational equilibrium, that the sum of the forces equals zero, and there's no net force on the object. Now we know from Newton's first law that just because the sum of the forces equals zero does not mean that, well, it means that there's no acceleration. Does it mean that the object's velocity is zero? No. We can have zero velocity, or the velocity could be some constant. I should just say some constant. Because if from Newton's first law we're going to have an object that's moving at a constant speed, there's no net forces on it, so its acceleration is zero, so we will continue moving at a constant speed. Okay, what we call this basically, and on the bottom of page 177, when we have this condition, we have what's called a static equilibrium. And when there's no velocity, when the object is truly at rest, we're in a static condition. Static condition means there's no motion, so the object is not static equilibrium. The object has no velocity. When the object does have a velocity, the object is moving, and so it's dynamically moving. So we call that dynamic equilibrium. Again, equilibrium again, implying that the sum of the forces is equal to zero. Okay. What we're going to go over now is on page 178 to 179, and really looking at an example, the example problem on 179 to 180 to 181, and really on up all the way to 185. Okay. The easiest condition, or the simplest condition that we can think of to have static equilibrium is when we have an object that's simply hanging from some beam. For instance, here's a ceiling, or this maybe is a beam, a rigid beam, and we have an object, some mass, and it's hanging from a, we'll call it, this is a rope. Okay. Now we know from gravity that the object, we can draw what we call a force diagram. Okay. I'm going to dot this. The rope is represented by this dotted line. There's two forces that act on this mass. And let's also assume that it's in static equilibrium, so the velocity is 0. This mass is just hanging by a rope. It's not moving. The weight acts down. The weight's equal to mg. Remember, the weight is a force, and it's mass times acceleration, where the acceleration is the acceleration of gravity. That's the weight acting down. To counterbalance that, there's what we'll call tension. The tension in the rope going in the up direction. So the weight acts down, the tension acts up. The sum of the forces are, we have tension, which acts up, and the weight acts down. The weight acts down, and let's use the idea that if a force acts up, it's plus. If a force acts down, it's negative. So the tension is a plus force, the weight is a minus force. These equal 0. The sum equals 0. Therefore, we know that the tension in the rope is equal to the weight, which is also equal to mg. So we have the very simple idea that basically the tension in the rope is equal to the weight. So think of a practical example. If we have, suppose it's holding a person, and the person weighs 150 pounds, okay, and suppose the rope has a weight limit of 200 pounds, say the weight limit of 200 pounds maximum, okay, we know that the rope can safely hold this person that weighs 150 pounds. If this weight, if the maximum rope tension, say, use a different rope and is 120 pounds, you put a 150-pound weight on it, you know what's going to happen. You have exceeded the weight limit of the rope. The tension in the rope actually will start to stretch the rope, and the rope can't withstand that, and it snaps. And so when we say tension is a force. Tension is a force, and it would be a tension, well, it's a force that is felt internally to the rope. Basically, every fiber of the rope is feeling this tension. If, as a matter of fact, we can diagram, if we diagram what we call a free body diagram, well, in fact, this diagram right here would be what we call really in engineering, what we call a free body diagram. It's really a force diagram that describes all the forces that act on a certain object. Okay? Just for diagrammatic or diagram purposes, and for the sake of understanding what's going on inside the rope, let's look closer at this rope. Suppose here's the rope. I'm going to expand the rope. Here's the mass with the weight acting down. Okay? Now, we know that there's a tension in this rope acting up. Tension in the rope acting up. But you say, what about a little piece of rope here? So what we're going to do, just to demonstrate how this works, suppose we take a little bit of the rope and we expand this out. We're going to, this rope right here, I'm going to expand this view of the rope, and in this box, here's that rope. It's just an expanded view. Now this rope has a little bit of mass to it. I'm just going to write that as little m. It's maybe not very much, but the rope has a little bit of mass. Now, is that rope moving in this case? No. We can actually do a free body diagram of the rope itself. Okay? What's happening to the rope? To this stretch of rope, say this is a 1 foot stretch of rope. This rope is not moving. It's stationary. So just like we drew a free body diagram here, we can actually do a free body diagram of this little piece of rope segment. Acting down, what do we have? We have acting down eventually is going to, this weight is transferred all the way up to here. Well, let me say this. At this point right here, there's a tension this way. And we know, suppose we collapse this rope, we know that this tension here is equal to the weight. This point here, there must be another tension acting up. Well, in fact, there is, because there's more rope up here. And we know that the sum of the forces acting on this little stretch of rope is that there's, I'm going to call this tension 1 that acts up. Tension 1 acts up, and tension 2 acts down, and that's equal to 0. We know that tension 2 is actually just the weight. So actually, tension 1 equals tension 2, which is equal to the weight. What this means is that every bit of rope, every little piece of rope, let's say if this is a little piece of rope, is feeling a stretching on it. Okay. Down this way is a tension acting down. There's two forces, one acting down, one acting up. Okay. So, and they equal to 0, so that because the mass is not accelerating. So we can actually, so this tension is actually acting through every little bit of the rope all the way up to the very point where it hits this beam. Okay. Let's go over an example on the example 6.1 on page 179. Actually, what I'm going to do is I'm going to jump over and look at the example on page 182. This is page 182, example 6.2. So I'm going to skip example 6.1 because they're quite similar. And example 6.2 is a little bit, has the angles are not equal. Anyway, we'll see. Here's example 6.2. We have a weight, a flower pot. This mass equals 5.00 kilograms, and it's held by two ropes right in the middle. Okay, this angle here is 30 degrees, and this angle here is 40 degrees. 40 degrees and 30 degrees. And, okay. Okay, when we have a problem like this, we have two ropes. This is a rope, and this is a rope. And this is a ceiling, or some kind of beam. There's two tensions. One tension acting this way, another tension acting this way. So the problem is find the tension in this rope and find the tension in this rope. Okay, so let's start off by drawing, again, a free body diagram. To do that, I'm going to put, we're going to call this T1, and we're going to call that T2. So our job in this problem is to find the tension T1, which is a force, and the tension T2, which is another force in these ropes. Now, this is really a two-dimensional static problem. So, first of all, we have and this is a two-step problem. First step is to look at the sum of the forces in the vertical dimension, and then we look at the sum of the forces in the horizontal dimension. In general, whenever you have a statics problem like this, that's exactly, or a static equilibrium problem like this, that's exactly what you do. You look at the sum of the forces in each dimension. So we know that acting down, the weight is acting down, which is mg. We know that that's acting down. Okay. So let's look at the sum of the forces. The sum of the forces in the horizontal, I'll call it x dimension. Well, what I'm going to do is to clear up just a little bit. I'm going to say, to clear this diagram up just a little bit, we know that the mass is equal to 5 kilograms. Theta 1 equals 30 degrees, and theta 2 equals 40 degrees. Okay, I'm going to assume that the mass is this little box here, and here's the weight acting down. And theta 2. I'm going to expand this just to make it easy to see. And I'm going to span this just to make it easy to see. Okay. The sum of the forces in the x dimension, that's the sum of the forces this way. Well, notice that there is a component of T1 acting this direction, and there's a component of T2 acting this direction. So as always, when we have a force problem like this, we will say, I'm going to say that if all the forces acting to the right are plus, and all the forces acting to the left are minus. That's just by convention. We could certainly flip that around and do it the other way, but we'll use that convention right now. I'm going to use a trig. If I drop a perpendicular from here, I can take this T1 and separate it into two components. I have an x component here. I'll call it T1x and T1y. Okay. The x component T1x, the x component, is simply T1 times the cosine of theta 1. T1 times the cosine of theta 1. T1y would be T1 times the sine of theta 1. Okay? That comes from chapter 3 and chapter 4, so by now you should have a good feeling of how to take a vector, a force like this, and to break it up into its x and its y components. In a similar way over here, I'm going to take this T2 force and break it up into T2x acting this way and T2y acting up. So in the x dimension, we have T1 cosine of theta 1 acting, that I'm going to say that acts in this dimension, to the right direction, and to the left direction, it's a minus sign, is T2 times the cosine of theta 2. And the sum of these equals 0. Okay? So that gives us one equation. Now notice, for right now we're just going to leave it in this form. We could certainly plug in theta 1 as 30 degrees and theta 2 as 40 degrees. But notice it's one equation, and there's two unknowns, T1 and T2. So if you have one equation and two unknowns, can you solve that? Can you solve for T1 and T2? No, we can't. But we have another equation, and that's that the sum of the forces in the y direction is also equal to 0. So let's look at the sum of the forces in the y direction. Acting up, we have actually two forces acting up. We have T1 in the y direction over here, and T1, T2 in the y direction over here. So the sum of these would be T1 in the y direction, which is sine of theta 1, plus, also acting up, is T2 sine of theta 2, and acting down is the weight of the object, and that equals 0. Okay? So, again, to summarize, in the y direction we have three terms. We have this tension in the y direction acting up. We have this tension over here in the y direction acting up. And both of these are counterbalanced by the weight acting down. So this tension is acting up, this tension in the rope is acting up, and the weight is acting down. And the sum of these must equal 0. So if you look at both of these two equations together, what we say is that we have two equations and two unknowns. The unknowns are T1 and T2. And if you know from algebra or linear algebra or from just mathematics in general, that essentially what we have are simultaneous equations, what we call in mathematics in more the realm of, I guess this comes under linear algebra, if you've had any linear algebra or just regular algebra, this is simultaneous equations. And so we have two equations and two unknowns, so this is a completely solvable system. That is, we can now solve for T1 and T2. We could do it algebraically, at this point we could plug in numbers or we could not plug in numbers, but what I'm going to do is show you just in general, actually just using algebra, how you can solve for this. There's two. Hopefully you've had enough algebra to know that in general there are at least one or two ways to solve these. There's several ways to solve an equation like this. Probably the simplest way to do it is to simply take one of these equations, solve for T1, and plug that into the second equation for T1 and solve for T2. So how would that look in a practical situation? That's what we're going to do. Instead of using numbers and plugging numbers in, I'm just going to leave it in the most general form. So let's take this first equation, which is really this. This is the first equation, and this is the second equation. Okay. Let's take the first equation and solve it for T1. So the first equation, T1 cosine theta 1 equals T2 cosine theta 2. So this implies if we divide by cosine theta 1, T1 equals T2 times cosine of theta 2 divided by cosine of theta 1. Okay? We can now, I'm now going to erase the first equation because now what we can do is we can take this for T1 and plug that into here for the T1 here. Okay? So I'm going to do that right in here. Instead of writing T1 though, I'm going to write this. So we would have T2 cosine theta 2 cosine theta 1 times sine of theta 1 plus T2 sine of theta 2, and then I'm going to put this to the other side, equals mg. Okay, I'm going to erase this. So at this point we have one equation now, and there's only one unknown, T2. So I'm going to factor out this T2, and I get T2 times, in large brackets, this term, cosine theta 2 sine theta 1. This looks a little confusing, but it's really not too confusing. Plus this term, which is sine of theta 2, and all of that equals mg. So all I've done here is to factor the T2 out of both terms. And what I'm left with are these trig functions plus that sine. So at this point now I can solve for T2. Again, I'm just keeping this in the algebraic realm. It's simply mg, the right-hand side of the equation, divided by, and I'm simply going to put what's in brackets. What's in brackets here, you simply plug right into here. Okay? So, in fact, I'm going to, well, tell you what, just for completeness, I will go ahead and write it out. Cosine theta 2 sine theta 1 cosine theta 1 plus sine theta 2. That's all added together like that. Okay, so what would this look like for the actual problem we were doing? Remember, M1 was 5.00 kilograms. If I remember right, theta 1 was 30 degrees. theta 2 equals 40 degrees. Okay? Really, when you solve this problem, the way I would do it is I would keep it in algebra all the way, algebraic form, all the way until I get my answer, and then I would plug in the numbers. A lot of students want to plug in the numbers early on, but to me it's easier just to solve it in algebraic form and then to plug the numbers in last. Me, more as a physicist and an engineer, it's more important how we derive these things. And so I'm actually much more, the answer is important. The numerical answer is important, but I'm really much more interested in knowing that you know how to get the answer, which means deriving and solving these equations. So actually, from an answer point of view, I'm much more interested in knowing that you know how to get this far, and if you just plug the numbers in and get the wrong answer, well, that's just plugging the number in and you just hit the wrong button on your calculator. That's no big deal. But the big deal is knowing how to write the equations and solving the equations. But for completeness sake, we'll go ahead and put the numbers in. We get 5, that's 5 kilograms times 9.8 meters per second squared over here, and I hope you all can see that.